So let's take a look at weight versus scale measurement. And just from a vocabulary point of view, if you're finding mass, it's really a balance. And if you're finding weight, you're really using a scale. And as we'll talk about in this, when you're finding weight, there are certain assumptions being made in order for the scale reading to actually be your weight. So in the very simplified view, when you start working in the first couple of chapters in a physics textbook, in beginning physics, just think you have a person on a scale on flat Earth. If you look at the force diagram here, we have normal force acting up because the scale is pushing up on the person. The weight of the person is acting down on the person because the Earth is pulling them down. And then the scale has a normal force from the Earth and from the person going in opposite directions, and the scale has its own weight. And so these are the forces acting on the Earth. Recognize that the force that the person exerts on the scale is this normal force right here, the reaction to that force right there, or the action to that reaction force right there. And if we look at the equation of motion for the person, we have yp, zooming up is positive, minus wp equals mass of the person times acceleration. So if the person is accelerating upwards, acceleration is positive. Downwards, acceleration is negative, given my convention there. If we do the equation of motion for the scale, we have this right here. We're not really concerned with that as far as this paper goes. That's the one that we care about the most. Now, if a person's in equilibrium, so the person just standing very still, what we would call static equilibrium, then the acceleration of the person is 0, and so the magnitude of that force is what the scale is measuring, and we assume that's equal to the weight. So all that seems very simple, and that's the basic assumption we're working with. However, let's bring a little bit more reality into it. One of the comments that I made on the previous page was that we had a flat Earth, but we don't have a flat Earth. Not only is it round, but it is rotating about some axis here. So the only places where you would not have to deal with this centripetal acceleration, because we are traveling in a circle, is at the poles. Now, if we do a force diagram now, we have weight acting down towards the center of the Earth. We have normal force pushing away from the Earth, and I am sort of assuming a sphere right now. And so they're not equal to each other because there is acceleration. Matter of fact, the acceleration isn't in that direction right there. The acceleration is this way because you are not traveling in the world around the center of the world like this. You're traveling around the axis like that. Since they are not equal and acceleration is in this direction, we have an unbalanced force here, and that also means that there would have to be then a net force in that direction, meaning that if the world were frictionless, you'd be sliding towards the equator. So there must be a friction force acting in that direction. So at this point, I'm only talking about the person, so I'm not going to worry about the subscript. So y is normal force, w is weight for acting on the person. Drawing it a little bit more oriented a little bit differently so that my axis of rotation is up and down, and I establish my I hat and j hat like that, and then I'm looking at the person at that moment right there, latitude theta. I break weight up into its components because, again, acceleration is in that direction, so I'm going to have to break up all three of them. And so I end up with w cosine theta to the right, y cosine theta to the left because it is in the opposite direction, w sine theta down, y sine theta up. Friction is perpendicular to them, and so the trig functions will switch, and so the vertical will have a cosine and the horizontal will have a sine, but here are the components of the three forces acting on the person. Now I know that acceleration is in that direction, so the f sine theta plus w cosine theta minus y cosine theta is equal to mass times the centripetal acceleration, and the forces in the direction must add up to 0 since acceleration is that way. This is perpendicular to the direction of acceleration. Manipulating just a little bit, we take that first equation, we separate the sines and cosines, and so the sine pieces I'll keep on the left side. I'll bring cosine over to the right side. So I have y minus w sine theta, factoring the sine theta out obviously, is equal to negative f cosine theta, or multiplying by a -1. We flip that subtraction problem and make that positive. So now on the second equation, I'm going to use omega squared for r. And so I have f sine theta plus, and then again, I'm going to separate the cosines and sine parts. So I end up with w minus y cosine theta for those two terms. So since the person is rotating about the Earth's axis of rotation around like that, r, the little r that was in the equation, because we had omega squared r, is just the radius of the Earth times the cosine of theta. This angle right here is also theta, because that and that are parallel to each other, and those are alternate interior angles. Omega is the angular speed of the person on the scale, and so that's just 2 pi, what's around, in a day. So in terms of seconds, 2 pi over 86,400 radians per second. So my equation, I had f sine theta plus w minus y cosine theta is n omega squared r. I can now make that substitution for little r to be r cosine theta. Separating the sines and cosines, so in other words, bringing this over to the other side, we end up with this relationship here. And then from our other equation, I can solve for friction by dividing by cosine and then end up with friction is equal to w minus y sine theta over cosine theta. Taking that, plugging it into there, we now have this equation right here, multiplying by cosine of theta to get rid of our fraction here. We have a sine squared still over here on this side, and on that side we now have a cosine squared. Sine squared is 1 minus cosine squared, so sine squared theta plus cosine squared theta equals 1. That's one of the basic identities of trig, and if you're not familiar, there's another video out there where I talk about that in a little bit more detail, or there's also math class. So w minus y times 1 minus cosine squared theta, so making that substitution is equal to this. Foiling, and then here distributing, and then ultimately, since the scale is reading that normal force, I solve for the normal force. So I'll get all the normal force terms on one side, the non-normal force terms on the other. Those cancel out, and I'm left with that as the normal force. So that is what the normal force is reading. So my weight, in other words, mg, is equal to that value. However, we have this other term right here. So putting this into actual numbers, my mass is roughly 100 kilograms, or if you've seen another video, it's a little bit less than that at the moment. It'll fluctuate. And I'm in Winston-Salem, North Carolina, or probably, what is the discrepancy between my weight and the scale reading because of the rotation of the Earth? So Winston-Salem, we have an acceleration due to gravity more exact than 9.8. My latitude is 36 degrees, 6 minutes, 9.95 seconds, which translates into this value for theta. I have this relationship here that we had derived on the other page. This is the discrepancy between what the scale reads and what my weight actually is, and that's equal to negative m omega squared re cosine squared theta. So plugging in my mass, 100 kilograms, and there's a little negative sign right there that don't want that getting lost. My angular speed, or at the axis of rotation of the Earth, is 2 pi radians, because that's the angle, divided by the amount of time it takes to do it, which is the number of seconds in a day. Radius of the Earth is, well, it depends upon where we are. This should be the distance from the center of the Earth to where I am, and so assuming that it is a spheroid shape, which the Earth is, because the distance from center to pole is different than center to equator. Not a lot of difference there, but there is some difference. This is the formula, and I just looked up the formula. You do a plug and chug, and we end up with, in Winston-Salem, that is my radius in meters. That is the distance from the center. And so using that for the radius of the Earth times the cosine squared of theta, where that is theta. Again, latitude is just the angle. If we slice open the Earth here, if this is the equator, latitude is just that angle from the equator to the center of the Earth to where you are. Doing plug and chug, we end up with negative, make that a little bit more pronounced, negative 2.1994 newtons. And so since my weight is mass times acceleration due to gravity, my weight is 979.8 newtons. And so the scale is reading a little over 2 newtons too low, or about 0.22% off. Now let's add a little bit more reality. Buoyant force. Buoyant force is another thing that is acting here. We have, just because I am in a fluid at the moment, the fluid happens to be air, there is a difference in the pressure from air coming from the top and from the bottom. And so I am buoyed up a little bit by that. So we have this extra force acting up on the person. And again, break it down into its components. The friction, the normal force, and the weight break up exactly the way they did before. But the buoyant force is in the same direction as the normal force, and so it's going to match the breakdown. So since we had y cosine theta, we have FB cosine theta, FB sine theta, y sine theta. Now, the acceleration is still to the right, so the sum of these forces is 0. The sum of these forces is mass times the centripetal acceleration, which I'm, again, using omega squared r, and all of this should be very familiar. Now, this is pretty much the exact same thing that we did before, except instead of y, we have FB. Since they're in the exact same direction, they're going hand in hand, and so if we go through the same math, we should end up with something very similar to what we had before. I had y minus w is equal to this, but now I have two forces in that direction. So it's now y plus the buoyant force minus w is equal to that same expression as we had on the other page. Subtracting buoyant force from both sides, we end up with y minus w is equal to this. So this is how much discrepancy there's going to be. This is what we figured out because of the rotation of the Earth. And the buoyant force, well, the buoyant force is equal to density times acceleration due to gravity times the volume of the person. My volume is roughly 0.1 cubic meters. We could get more precise there. That's rounded off. And so not all of these are significant, but I'm going to pretend anyway. So I have 1.21 kilograms per cubic meter. That is the density of air at 20 degrees Celsius. There's the acceleration due to gravity where I am, and times my volume, and I end up with that amount. So I subtract that also. Again, not all significant, but it's pretty close. 3.385 newtons is negative, is how far it is off. So the scale is reading 3.385 newtons too low, or it's off by about 0.345%. And very crudely, this is about 3/4 of a pound. So your actual weight is 3/4 of a pound more than what the scale shows. Now let's take it that one step further. Suppose you want to lose what the scale reads, in other words, apparent weight. There are some textbooks that will say weight is whatever the scale reads, that this actually is the weight. I think that's a minority. If you look at definition of weight, it's usually defined as gravitational pull. And so apparent weight is what the scale actually reads. And so taking our equation, solving for the normal force, if I want to lose my apparent weight, I either need to drop my weight or increase these two values. I have three different ways that I thought of right here. I can get farther from the center of the Earth, which makes g smaller. This causes a loss of actual weight. It does not cause a loss of mass, but it does cause a loss of weight. I can get farther from the pole or closer to the equator. So in other words, theta gets smaller, and as theta gets smaller, this term right here gets bigger. Also, RE gets bigger as I get closer to the equator. And so that term would increase if I get closer to the equator. And also getting into colder air to increase the density of air. And as the density of air increases, the buoyant force increases. And so these are ways that I can lose my apparent weight. There's also jumping on the scale too. However, any quick loss of apparent weight by jumping on the scale is met by just as much gain in apparent weight. And that's for those of you who still use analog scales.